The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Now, firstly, what does the formal charge tell us? Well, as it says here, the formal charge informs us of whether or not an atom in a molecule gains or loses an electron relative to the atom in its isolated form. For example, once you find the number of valence electrons in the atom in a molecule from the Lewis electron dot structure, and you compare that to the isolated form of the atom, and if the if the valence electrons are not equivalent for the two atoms, then the atom in the molecule has either gained or lost electrons, and it is therefore said to have a formal charge. Now, if the atom in the molecule gains electrons, then it's gonna, as you might expect, have a negative formal charge. And if it loses electrons, as you might expect, it's gonna have a positive formal charge. Now, we'll skip over the second bullet, although it is important. We'll come back and take a look at this in just a moment. Next, we'll take a look at calculating the formal charge of an atom in a molecule. And to do so, it's fairly simple. All we're going to need to do is just take the number of valence electrons in a free atom minus the number of valence electrons in the bonded atom. And the valence electrons in a bonded atom can be found through the following formula, which is just the number of non-bonding electrons plus 1/2 of the number of bonding electrons. Let's do an example now on the next slide to really solidify our understanding here. Example: formal charge. Assign a formal charge to each of the atoms in tetrafluoroborate ion. Now, we're given the formula as well as its connectivity here in figure 20. Now, we'll begin here with fluorine. We'll find the formal charge for fluorine, and then subsequently for the boron atom. Now, for fluorine, let's first go ahead and find the number of valence electrons in a free fluorine atom. Well, we know that fluorine is a main group 7 element, thus a neutral fluorine atom is going to have 7 valence electrons, right? And as you see here, it has 7 valence electrons in a free atom. Next, let's find the number of valence electrons in a bonded fluorine atom. And that's simply just going to be the number of non-bonding electrons, right? And as we see here, each fluorine atom has 6 unshared electrons, right? Right there. There we are. So that's going to be, I'll just write it up here, 6 plus, and it also donates 1 electron for the covalent bond as well, right? So it donates 1 electron for the covalent bond, as we see here, which is just simply the 1/2 of the number of bonding electrons. 6 plus 1 is 7. Now, because each of these fluorine atoms, as we see here, they are equivalent to one another, we can then just say that the formal charge, right, for the fluorines is simply just going to be the valence electrons in a free atom, 7, minus the valence electrons in the bonded fluorine atoms, which is 7, the formal charge is just simply going to be 0. Now, we should also note that the sum of the formal charges for all the atoms should equal the charge on the ion. And we see here that the charge on our ion is 1, right? Is 1. Therefore, that -1 formal charge must be on the boron atom. Now, because of the fact that we know that fluorine's formal charge is 0, thus this -1 formal charge must be on the boron atom. Let's proceed to our next slide and take a look at that. All right. Now, here we'll begin here with boron and finding the number of valence electrons in a free atom. We know that boron is a main group 3 element, thus a neutral boron atom is going to have 3 valence electrons. Now, the valence electrons in a bonded atom, well, here, as we see, boron does not have any non-bonding electrons. However, boron does have, it's going to 1/2 of the bonding electrons. Boron does participate or contributes 1 electron to each of the covalent bonds for a total of 4 electrons, right? Thus, the number of valence electrons in a bonded boron atom is going to be 4. And the formal charge for boron is simply just going to be 3 minus 4, as we see here, is going to be -1, as we had predicted on the previous slide. Now, when you're going to be indicating the formal charge on a compound, you can do so in one of 2 ways. You can do so by indicating the formal charge right on the atom, as we've done here on our example to the right, or it can be demonstrated as an overall charge on the for the entire ion, as we see here, given on the left here. Either example is acceptable. Now, the real value of calculating formal charges comes from their application to resonance structures. Let's take a look at that next. Remember that second bullet that we had left alone? Let's take a look at that now. As it says here, formal charge, it aids in determining the relative stability of resonance structures. Let's do an example and really explain what that means. Okay, taking a look here. Here we're being asked, what is the more favorable Lewis electron dot structure for nitrous oxide? Is it going to be A, B, C, or D? Let's do an explanation actually on the next slide here. Now, looking here at figure 22, we see that we're given all 3 resonance forms for the nitrous oxide. Now, because all 3 forms are not identical, one of the 3 forms here is actually going to contribute the most to the actual structure and chemical reactivity of nitrous oxide. And more generally speaking, the resonance hybrids are always weighted more strongly towards the more favorable structure. Now, in order for us to find the most favorable Lewis electron dot structure for nitrous oxide, next what we're going to need to do is we're going to need to ascertain the formal charge on each ion here for each resonance structure. Now, we've already gone ahead and given the formula in the previous slides. Thus, this would be a great time for you to pause the video and really sharpen your skills on finding the formula, the formal charge on atoms. Thus, I'm going to encourage you to pause the video now and attempt that. Now, for the rest of us that are comfortable finding the formal charge, what I'm going to do is I'm just going to go ahead and continue and display the answer now on our slide here. And there we are. The formal charge is given to us right up here. Now, notice one thing, that the sum of the formal charges for each structure is equal to 0, and that makes sense, right? Because the charge should equal the charge